today we are going to be looking at all the maths required for A-level physics. This video will be particularly useful if you're doing A-level physics but not A-level maths. It will also be useful if you still haven't quite mastered some of the concepts that we're going to be discussing. Now, what is this video all about? Now, the topics that I'm going to be looking at, I've numbered them here 1 to 7. 1 to 4 are typically encountered in the first year. This can vary from college to college. However, normally rearranging equations, powers and exponential, linear y equals mx+c analysis, resolving and adding vectors are commonly taught in the first year. In the second year, we use 1 to 4, but also we use radians, we use logarithms, and also we convert logarithmic equations into y is equal to mx+c form. Well, let's get started with number 1, rearranging equations. So let's do some rearranging. The secret to rearranging is realizing that an equation means that the left-hand side has got to be equal to the right-hand side. If that's the case, whatever we do to the left-hand side has got to equal whatever we do to the right-hand side. For instance, if we wanted to rearrange V is equal to IR for the resistance R, what we need to do is to divide both sides by I. How do I know that? Well, if I was to divide this side, the right-hand side, by I, what I'm going to get is I cancelling out and only having R. So what I'm doing is literally dividing both sides by I. What I'm left with after I cancel out the I's is that V over I is equal to R. And I'm done. Question 2. V is equal to U plus AT. We want to rearrange for A. Now, the first thing that we need to do is just really make sure that we only have AT on one side of the equation. So one way to do that would be to take away U from both sides of the equation. Now, if we take away U from the right-hand side, we're going to have U plus AT minus U, and this will be equal to V minus U. We can immediately cancel out the U's, and what we're left with is that V minus U is equal to AT. Now, this step is often very much skipped when you are solving problems because you get so used to the idea that if you have V being equal to U plus AT, if you were to bring the U on the other side of the equation, it will turn to a negative. So what we get is V minus U is equal to AT. Our final step would be to rearrange for A, and in order to do that, we must divide both sides by T. So what I'm doing is literally just dividing both sides by T, like that, and notice that the T's are going to cancel, and what I get is that V minus U divided by T is equal to A. Question 3. So we have Kepler's third law, T squared is equal to 4 pi squared R cubed over GM. What we need to do is rearrange for R. Okay, well, what we're going to do now to the right hand side of the equation in order to only have R cubed would be to multiply both sides by GM. So should we just write this? So multiply by GM, and that applies to both sides, and we're also going to divide by 4 pi squared. Okay, so what we're left with is going to be GM T squared, and we're going to be dividing that by 4 pi squared. Okay, so let's just copy down what we have. So that's 4 pi squared R cubed over GM, and let's do what we did on the left hand side of the equation to the right hand side. So we're going to multiply this by GM, we're going to divide this by 4 pi squared, like that, and we can see that what we're left with is r cubed. So what we have is that r cubed is equal to gm times t squared divided by 4 pi squared, and our final step will be just to cube root this. So this is equal to the cube root of gm times t squared divided by 4 pi squared. Let's do 3 more examples. It'll be perfect if you guys could just pause this video and then check with my solutions in a second. So please go ahead and pause that video. Okay, well, let's have a look at the solutions. So question 4, we need to rearrange for theta 2. This is an example actually of something called Snell's law that we do in the first year of physics. So let's rearrange for sine theta 2. What I'm going to do is divide both sides by n2. So n1 sine theta 1 divided by n2 will be equal to n2 sine theta 2 divided by n2, but the n2's are going to cancel out, so what I'm left with is just sine theta 2. Now my final step would be just to rearrange for the actual angle. So remember, this is sine of the angle. The way we do that is using the inverse sine functions, and we can just write down that theta 2 is equal to the inverse sine of this whole expression that's on the left hand side. So n1 sine theta 1 divided by n2. Okay, well, question 5. So r is equal to rho times L divided by A. So this symbol here, it's often used to denote resistivity, but also density, and it's pronounced rho. Okay, so we need to rearrange this for A. The first thing that we need to do is bring A up here to the denominator of the fraction. So the way we're going to do that is by multiplying both sides by A. So let's multiply the left and the right by A. So what I'm going to get is that R times A is equal to rho times L times A divided by A. So literally what I've done is I've multiplied the left by A, and because it's an equation I have to multiply the right as well. The A's are going to cancel out, and what I'm left with is that R times A is equal to rho times L. The final step would be to divide both sides by R. In this case, the R's are going to cancel, and what I'll be left with is that A is going to equal to rho L divided by R. Question 6, so v1 over v2 is equal to r1 over r2, and we want to rearrange for r2. A good useful multiplication trick that I still often use is known as cross multiplication. It essentially means that this times this equals this times that. So v1 times r2 will be equal to r1 times v2. So it's essentially like drawing a little x. So v1 times r2 is going to equal to r1 times v2. Okay, well, if we want to rearrange for r2, all we need to do is divide both sides by v1. So what I'm going to be left with, let's divide both sides by v1 like so, and the v1s are going to cancel out here, and what we're left with is that r2 is equal to r1 times v2 divided by v1. Okay folks, well those were some of the main problems that we experience in rearranging equations. However, I have to say that rearranging equations is all about practice. So we need to practice rearranging all of these formulae as many times as possible until it becomes second nature. Now let's look at number 2 on the list. Right, on to number 2, powers. Let's start up with negative powers. Very often in A-level physics, you're going to find that we write numbers such as 9.81 meters per second squared, rather than divided by second squared, we would often tend to write them as 9.81 ms raised to the power of -2. This is because any fraction, for instance, let's say 1 over, I don't know, time cubed, we could write this, or 1 over seconds cubed, we could write this as s to the power of -3. For instance, if we had 1,000 kilograms per meters cubed, this would be equal to kilograms m to the power of -3. The rules for multiplying and dividing powers as well are as follows. We tend to use those quite a lot. Meters squared times meters cubed. Well, all we need to do really is add the powers. So this will be equal to m raised to a power of 2 plus 3. So it's going to give us m raised to the power of 5. If one of those powers is negative, that's not a problem, we just subtract them. So m to the power of 2 times m to the power of -3, this will be equal to m to the power of 2 minus 3, which is equal to m to the power of 1. Finally, for instance, if we had, let's say, seconds to the power of 2 divided by seconds to the power of 3, well, this will be equal to s to the power of 2, but because we're dividing by s to the power of 3, we could write this as times s to the power of -3. So overall, this will be equal to s to the power of 2 minus 3, which is equal to s to the power of -1. Let's do an example and just see how those rules are applied to a problem in physics. For instance, here's a very common problem: find the base units of pressure. Pressure is force divided by area. Force in general is equal to mass times acceleration divided by area. Now, the units of mass are kilograms, the units of acceleration are meters, s to the power of -2. The units for area, on the other hand, are m to the power of 2 meters squared. So what we're left with is kilograms, meters divided by meters squared, s to the power of -2. So this will be equal to kilograms, meters. Now, if there's no power, then this will essentially be equal to 1 minus 2. So it'll be meters to the power of 1 minus 2, and 1 minus 2 is, of course, m to the power of -1, and then s to the power of -2. Powers can also be quite a common mistake when we're dealing with some calculations. For instance, let's have a look at this one. Let's find the cross-sectional area of a wire with a diameter of 0.4 millimeters squared. Now, the area of a circle is given by pi r squared. However, we're not given the radius, we're given the diameter. So a way of writing this formula in terms of the diameter is pi d over 2 in brackets, and then this whole expression of d over 2 is squared. So let's proceed with that. The area will then be equal to pi, and the diameter is 0.4 millimeters. Remember, milli stands for 10 to the power of -3. We're going to divide that by 2, and then we're going to square this whole expression, 0.4 times 10 to the power of -3 divided by 2, with our calculators. The area will then be equal to approximately 1.26 multiplied by 10 to the power of -7 meters squared. Next, I would like to give you a little power trick that can allow conversions to happen a lot quicker. For instance, if you want to convert 5 centimeters squared to meters squared, the trick is to realize that the square acts both on the centi and on the meter. So 5 centimeters squared is actually equal to 5. Well, centi stands for 10 to the power of -2 times meters squared, which is equal to 5 times. Now, 10 to the power of -2 raised to the power of 2 will give us 10 to the power of -4 meters squared. We can apply this trick to any power and any prefix. For instance, if we wanted to convert 10 millimeters cubed to meters cubed, what we get is 10. Now milli is 10 to the power of minus 3 meters. So all we need to do is just draw some brackets, convert the prefix to a power, and then cube everything. So this will be equal to 10 times 10 to the power of minus 3 times 3 will be 10 to the power of minus 9 meters cubed, like so. Which is of course equal to, let's leave that as 10 to the power of minus 8 meters cubed. Now on to the next skill that we need to revise, and that is linear analysis. First off, we absolutely must be able to find the gradient of a graph. For instance, I have a graph here of voltage against current. The first rule that we need to remember is that we always need to look at the units of the graph. Very often we may have non-standard units. For instance, here we just have volts, which is fine, but down here we have milliamps. The second rule is that whenever we are looking to find our gradient, we need to use as large of a gradient triangle as possible. For instance, my gradient triangle in this case is pretty much all the way along here, and that is as large as possible. So let's actually calculate the gradient. Now I'm going to call my gradient m, and this will be change in y divided by change in x. A good way of remembering this is rise, change in y, divided by run, or rise over run, divided by delta x. So let's do some calculations. Our delta y will be equal to y2 minus y1, and our delta x will be equal to x2 minus x1. Now our y1 and x1 are actually going to be 0 because the graph starts from the origin. If it didn't start, we'll have to include a value and take that away too. So, but in this case, our y2 is going to be 20, and then I'm not going to write minus 0 because y1 is equal to 0. Then I'm going to be dividing that by let's see what the value is. So the midway point is 27.5, so just before that, call that 27 milliamps, so that will be times 10 to the power of minus 3. When we put that into a calculator, we find approximately 740 ohms for our gradient. How did I know that the units of the gradient are equal to the units of resistance? Let's have a look. The equation that links voltage and current is Ohm's law, which is that V is equal to I, the current, multiplied by the resistance. Let's compare this to the equation of a straight line, which is y is equal to mx plus c. Y, of course, in this case is the y coordinate, m is the gradient, x is the x coordinate, and c is the intercept. Now we can add a little plus 0 algebraically to pretty much any expression. Notice that this graph here is a straight line through the origin. So let me just write this because this comes up a lot in explanation questions. So the graph is a straight line through the origin, and this tells us that V is proportional or directly proportional to I. It also means that we can apply y equals mx plus c analysis. So if V is on the y-axis, if I is on the x-axis, our intercept will be 0. What is left for our gradient is the resistance. So our gradient m is equal to r, which is the resistance. Right, on to our next y equals mx plus c example. We have an equation here, which is the centripetal force equation, and F is equal to mv squared over r. We do that equation in the second year. However, in an exam situation, you may be given an equation that you've never seen before, that is not necessarily on the specification. If that happens in an exam, do not worry. You can handle this question. All you need to do is follow a couple of really simple steps that we're going to go through now. So a student performs that experiment involving a rotating bung on a string, keeping the force constant, varying the radius, and measuring the speed. The student plots a graph of v squared against r. What would the gradient of this graph be? So our first step would be to rearrange for whatever is on the y-axis. So for instance, here we have v squared on the y-axis, so I'm just going to rearrange this equation for v squared. So in order to do so, I need to divide by m and multiply by r. So what I'm going to get is that f times r divided by m is equal to v squared. Okay, so let me just write this down here. V squared is equal to fr divided by m. And this is our equation correctly rearranged for v squared. Now what we need to do is compare this equation with the equation of a straight line, y is equal to mx plus c. So what I'm going to do is just copy this. So v squared is equal to fr divided by m. I'm going to add a little plus 0 over here, and what I'm going to do is just write down y is equal to mx plus c. However, because I'm already using the symbol m for the mass, I'm just going to write gradient times x plus c. So if v squared is on the y-axis, if r is on the x-axis, if my intercept is 0, well, this means that everything else that is multiplying the x-axis will be the gradient. In this case, this quantity f over m is actually going to be equal to our gradient. So we can write this down as our gradient is equal to f over m. Once again, in explanation questions, quite often they would ask us what sort of shape we might expect, and what we can always write down is that the graph is a straight line through the origin. So the graph is a straight line through the origin as v squared is proportional to r when everything else is a constant. Let's do one more example of y is equal to mx plus c analysis. Once again, we've not covered these equations yet in class. Do not worry, these are just mathematical equations, and if we wanted to, we could apply y is equal to mx plus c analysis to almost anything. So we're given the equation hf is equal to the work function phi plus the maximum kinetic energy. If we have the kinetic energy on the y-axis and we have the frequency on the x-axis, what are the gradient and what is the intercept? Okay, well, remember, our step one is to rearrange for whichever quantity is on the y-axis. In this case, that's k max. So this is what we're going to do. Ke max will be simply equal to hf minus phi. Okay, well, right underneath, let's write down y is equal to mx plus c. Our kinetic energy is on the y-axis, our frequency is on the x-axis. We're expecting our intercept to be negative, which it is, and our intercept will be minus phi over here. Our gradient, what's left for our gradient, is the constant h, which is actually Planck's constant, so we can highlight this in yellow. So in this case, our gradient is equal to the constant, and our intercept is equal to minus phi. And final y is equal to mx plus c example. So let's apply y is equal to mx plus c analysis in this situation. Find the gradient and then the intercept. We're given this equation that epsilon, which is the EMF, is equal to v, which is the terminal PD, plus I times r. Once again, if you've not done this equation yet, do not worry. We'll just be looking at the symbols behind it and applying the maths. We have a graph of v against I. So our first step is to rearrange for whichever quantity is on the y-axis. So in this case, this is v, and v will be equal to the EMF epsilon, take away I times r. Now let's apply y is equal to mx plus c analysis. Because I can see that I is on the x-axis and the equation is y is equal to mx plus c, just to make this a little bit easier to compare with to y is equal to mx plus c, what I'm going to do is I'm just going to swap the positions of those two terms. So I'm going to write minus I r plus epsilon. Okay, well, if v is on the y-axis, like so, if I is on the x-axis, and if my intercept is the EMF, what I've left for my gradient are two things. So there are two things which are multiplying I. You have minus, this minus sign, and you have minus r. So our gradient is equal to minus r. Quite a typical mistake is to forget the minus sign, and our intercept c is equal to the EMF. So if, let's say, this was, say, 5 volts, this data point here, then this will be the value of our EMF. Our gradient will be equal to the negative r. We can already see that the gradient is negative as well because it's slanting downwards. Now let's have a look at resolving vectors. Remember, vectors are quantities which have both a direction and a magnitude. For instance, velocity. Imagine that we shoot off a projectile 5 meters per second at an angle of 35 degrees to the horizontal. We can represent this motion by two vectors that are perpendicular to each other. The horizontal component, how much does the projectile move horizontally, and how much does it move vertically. I've called these components Vx and Vy. Now we can find Vy and Vx pretty easily using some trigonometry. Vy will be equal to the value of our hypotenuse, which is 5, times the sine of the angle. So the opposite component will always be equal to the value of our hypotenuse times the sine of the angle. In general, let's say that this here was v, and what we wanted to do is find Vy and Vx. So Vy will be equal to V sine theta, and Vx will be equal to V cos theta. I have proven this relationship using simple trigonometry on the main videos that I have on vectors. So if you're unsure about where this comes from, please have a look through the playlists, and under module 2 foundations of physics you're going to find quite a few of my vectors videos. Anyway, so Vy will be 5 sine of 35, which is equal to 2.9, and Vx, which is the horizontal component, will be equal to 5 cosine of 35. Now notice that I've said that it is always the adjacent component, which is the cosine, and the vertical component is found, or the opposite component is found by multiplying by the sine. You could get a little trick sometimes. For instance, if you look at this vector here, you have the force which is pointing downwards, and you're given this angle here. Well, the adjacent Fy will actually be given by the cosine. So in this particular example, Fy will be given by F cosine of theta, and the horizontal component fx will be given by f sine of theta. So just ask yourselves if the horizontal component is opposite or adjacent, and then use either the sine or the cosine function. And just a little note that if you're revising how to add vectors, I have quite a few videos on that topic, and if you're revising this, have a look in the links in the description. Okay guys, we're doing excellent progress on to the next item from our list, which are radians. Now the radian is actually the SI unit for an angle. It's normally derived from essentially the definition of an angle, that the arc length S, so this guy over here, S, is actually the arc length, is equal to the radius R. Let's be consistent, I'm just going to write this with lowercase r, times the angle theta. Now to change from radians to degrees, or to convert from radians to degrees, all we need to do is multiply by 180 and divide by pi. So for instance, let's say that I had 2 pi radians. If I'm going from radians to degrees, all I need to do is multiply by 180 and divide by pi, and I get that 2 pi is actually equal to 360 degrees. Now 2 pi is generally one complete rotation or a full circle. If I'm going from, let's say, 90 degrees, so all I need to do is, following this, multiply by pi and divide by 180. So if that's the case, well, let's just divide. So that's going to be equal to 1 over 2. So in fact, let's get rid of this. This will be equal to just pi over 2 radians. Before we move on, just a little reminder that there are a couple of equations that only work if our calculator is in radian mode. In simple harmonic motion, so this is simple harmonic motion, which is a topic that we do in the second year, x is equal to a cosine omega t and x is equal to a sine of omega t. So if that's the case, what we need to make sure is that our calculator is set to radians mode. For instance, if I was to calculate, let's say that the amplitude is, I don't know, 5 meters, and I want to do the cosine of, let's say, it has an angular frequency of 4, and let's say that I was interested in at time is equal to 0.1. If I was to input this into a calculator, I should be able to get 4.6 meters, and if I'm getting a strange answer, chances are that my calculator is in degrees mode. So those two equations, remember that you need to ensure that your calculator is in radian mode. Now let's start talking about logs. Now logarithms can sometimes appear tricky, but I literally think that that's just a matter of the fact that they use quite a lot of symbols, but the actual logic behind logarithms is not that complicated. So let's have a look. If we have any quantity, let's call that, I don't know, a to the power of x, rather than just jumping into the problem, I'm going to have a look at this regular solution. We can have a function which is the inverse function of raising something to the power of x. For instance, I don't know, division and multiplication, they're inverse functions. If I multiply x by 2 and if I divide x by 2, I'm going to get x. In exactly the same way, I can raise a to the power of x, but I can also do something else which is just going to give me x. So for instance, if I was to take the logarithm base a, as this is called, what I'm going to get is x. So this is defined as x. You can take the logarithms on either side of the equation. For instance, let's have a look at this problem. 2 raised to the power of x is equal to 1024. Well, remember, log base a of this quantity a is actually going to give me x. So what I'm going to say is that log base 2 of 2 to the x, well, this will, if we've done this to the left hand side, we need to do this to the right hand side as well. This will be equal to log base 2 of 1024. Now this would mean that x, because remember the logs are inverse functions if the two bases match, so they kind of undo each other. So log 2 and 2 to the power of something, they undo each other. So x will be equal to log base 2 of 1024. We can literally put this into our scientific calculator. Look out for the log button, which allows you to input both the base and the actual number. And if we plug in log 2 of 1024, we're going to find that x is equal to 10. And of course, well, this is because, or i.e., 2 raised to the power of 10 is equal to 1024. Let's do one more log example. So we have the following equation: 10 raised to the power of x is equal to some large number, 1.57 times 10 to the power of 8. Remember, in order to find x, what we need to do is take the logs of both sides, and I'm going to take log base of 10 to the x, and this will be equal to log base 10 of 1.57 times 10 to the power of 8. Log base 10 and 10 to the power of essentially cancel each other, so what we're left with is that x is equal to log base 10 of 1.57 times 10 to the 8. Just a little word of note that in OCR physics, so if you're doing OCR physics, log base 10 of something, let's call it, I don't know, something, is denoted as simply LG to save some space. So what I'm going to say is that x is equal to log base 10, which is LG, of 1.57. Oh, there's an extra dot here, so let's fix that, of 1.57 times 10 to the 8. This LG can be a little bit confusing, but all it is log base 10 of that number. What I want you guys to do is just put that in your calculator. So log base 10 brackets 1.57 times 10 to the power of 8, or LG 1.57 times 10 to the 8, and what we're going to get is 8.195 or so. In practice, this means that if we raise 10 to the power of x, let's say 8.195, and we can put that into a calculator if we wanted to, we would get approximately up to a few significant figures, 1.57 times 10 to the 8. Adding and subtracting logarithms can be a little bit counterintuitive. We're given some formulas in our physics data sheet. Actually, there's quite a lot of mathematics on there, so have a look at the first couple of pages if you are a little bit unsure. Now, if we had a logarithm of any base of a times b, where a and b are just two numbers, this is actually equal to the log of a plus the log of b. The log of a divided by b is equal to the log of a, take away the log of b. If we were to raise a log to the power of n, then this is equal to n times the log of x. What I would like to introduce you to now is probably the most important logarithm in physics, and that is the natural log. The exponential function is crucial in physics. In the second year of physics, we use it when we're talking about capacitors. Later on, we use it in nuclear physics as well. It can appear in simple harmonic motion and in virtually all areas in physics. Now, e to the power of x, if we're interested in x, we would need to take the logarithm base e. Rather than writing log base e all the time, we've given this a special symbol, which is ln, and this is simply log base e of some number. So if that's the case, ln of e to the power of x will actually be the inverse function, and what we literally can do is write down that ln of e to the x is actually equal to x. Now let's apply what we've learned so far to quite a typical derivation. So we have the equation v is equal to v naught e to the minus t over cr, and our job is to rearrange for t. Well, our first step will just be to put the exponential to one side. So I'm going to divide both sides by v naught. So I'm going to write down that v over v naught is equal to e to the minus t over cr, like that. Now what I'm going to do is simply just take the logarithms of both sides. I'm going to take the natural log of both sides. I'm going to do ln of v over v naught is equal to the ln of e to the minus t over cr. And what we can do afterwards is write down on the left hand side we have ln of v over v naught, so this is actually equal to ln of v minus the ln of v naught. Remember, this was the rules for dividing logs, we take them away, and this will be equal to ln of e to the minus t over cr. But hang on a minute, ln of e to the x is just equal to x, so our x in this case here is actually this whole expression. So in other words, what we're going to get if we take the natural log of e to the minus t over cr is simply minus t divided by cr. What I'm going to do is multiply both sides of the equation by -1, and what I'll get is ln of v naught minus ln of v is equal to t over cr. So the minus sign actually flips this ln. So I can return this to fractional form by saying that this is equal to ln of v naught divided by v. And this is equal to t over cr. And let's fix this, cr. And my final step would be to simply rearrange for t, which will be equal to the natural log, or ln, of v naught over v multiplied by c times r. And we've successfully managed to rearrange for t. Another example of using exactly the same mathematics is in nuclear physics in the second year, when we deal with the half-life. The decay equation in nuclear physics is that the number of particle n's at time t is equal to the initial number of particles times e to the minus lambda t, where lambda is the decay constant. Well, what we can do once again is simply rearrange for n over n naught, and this will be equal to e to the minus lambda t. Now let's take the ln of both sides, so that will be equal to ln of n over n naught. Now if we were to take the ln of e to the minus lambda t, what we're going to get is simply minus lambda t, so that's what I'm just going to write down. So this is equal to minus lambda t. Now let's think about this ratio. Actually, just before that, let's multiply everything by -1. So this will then be equal to lambda t, and due to the properties of taking away logs and dividing them, if we were to multiply by -1, then we essentially flip the fraction. So this will be equal to ln of n naught over n is equal to lambda times t. Now, when t is equal to the half-life, I'm going to write this as t half, like that, then the fraction of the number of particles initially over n is equal to 2. So what we're left with is that ln of 2 is equal to lambda t. And this is a formula and a classic derivation that may come up at an exam. This number ln of 2 is actually equal to 0.69, so an additional way of writing this equation down is just simply 0.69 is equal to lambda t. But in general, our half-life, let's call it t half-life, like so, t half-life. This is just a subscript, by the way, this half, it has nothing to do with the maths, it is just a symbol, will be equal to ln of 2, or 0.69, divided by our decay constant, lambda. Okay guys, final question in this Maths for Physics revision lesson. So let's apply y is equal to mx plus c analysis to plot a graph of ln of v against t. Just a little note that anytime that you see a logarithm graph in experimental questions, chances are that it's going to be divided by the unit. So if you see an ln of v over v, don't worry, that's not like the log of 1, for instance. It's literally the log of voltage, or the ln of voltage, divided by the unit volt, because it needs to be a unitless number. Now that we've got this out of the way, let's just apply our normal natural log rules for this question. So first off, I'm going to just put the exponent on one side. So we're going to get v over v naught is equal to e to the minus t over cr. Then I'm going to take the natural log, or the ln of both sides. So what I get is ln of v over v naught, and this will be equal to the ln of the right hand side, so that's going to essentially cancel out the exponents, so this will be equal to minus t over cr. Well, remember, ln of v over v naught is actually ln of v minus ln of v naught, and this will be minus t over cr. So we can directly rearrange for ln of v. ln of v will be equal to minus t over cr plus ln of v naught, the ln of our initial voltage. Now we're ready to apply y is equal to mx plus c. So y is equal to mx, where m is the gradient, plus c. If ln is on the y-axis, if t is on the x-axis, if our intercept is the natural log of the initial voltage, then what we're left with for the gradient is whatever is multiplying t. So we have a minus sign multiplying it, and 1 over cr as well. So our gradient will be minus 1 over cr. Our intercept c will be equal to ln of v naught. Okay folks, well, this was quite a long revision lesson, but we've covered the vast majority, in fact probably all important concepts that we use constantly in A-level physics. Hopefully you found this video useful. Thank you very much for watching, and I'll see you in the next video.